So up next is another big theorem of multivariable calculus. So where does it come from that might help us understand where we're going? So previously, we looked at a form of the fundamental theorem of calculus, Green's theorem. And Green's theorem gave us an equation between a line integral of a two-dimensional vector field on a closed path with a double integral over a two-dimensional region. So that looked like this. Let me not split that up. There we go. Okay, so the line integral over C of f dot dr is a double integral over the region of the swirl of FDA, where of course the curve C is the boundary of the region R. Okay, so now we're going to take that and we're going to extend it to parametric surfaces in 3 dimensions. So basically everything in that formula will kick up a dimension. So the vector field will now be 3-dimensional, and the region is now going to be a surface. So I shouldn't say kick up dimension. I should say we're now going to have everything parametrized. So let's take a look. So this brings us to Kelvin-Stokes theorem, which is sort of the more general version of Green's theorem that we've seen before. So we get the integral over the curve of f dot dr equals, and now we are again doing a double integral over a 2-dimensional thing, but that 2-dimensional thing is now a 2-dimensional surface with a parametric equation. And once you're in 3 coordinates, we can only talk about the swirl. Swirls for 2 variable vector fields. So that derivative operator, that vector field operator, is now curl, and dA becomes ds. Okay. Now, just as with Green's theorem, it must be true that, first of all, the path C must be closed on the left side, and on the right side, you've got some vector field in there. That vector field must wind up being the curl of some other vector field. Okay, so that is one difference. Swirl of f previously was a scalar. This is now a vector. Now, for obvious reasons, this theorem is also called the curl theorem. And I'll also mention that this theorem is sometimes mistakenly referred to as Stokes theorem. Stokes theorem itself is actually the name of a more general theorem for which this is a special case. And we will generally use the Kelvin-Stokes theorem in this form, but let me mention that because of what we know about vectors, it can be written in a different fashion as well. So remember that we know another way to write dr is unit vector t ds, and our other way of writing ds, where s is the oriented surface, is unit vector n ds. So just making those substitutions, here's another way to write the Kelvin-Stokes theorem. Okay, so there's the theorem, and let's take a look at an example to see how to use it. Okay. So here's a vector field f, 2z comma x comma y squared, and then surface S, z equals 4 minus x squared minus y squared. And we're going to take z to be positive. And the curve C is its boundary, and we'll take everything with the usual positive orientation. So what we're going to actually do is we're actually going to verify the Kelvin-Stokes theorem by calculating both sides. We're going to calculate both the line integral over the curve and the double integral over the surface. So let's take a look. And if we do everything right, we'll get the same answer either way. So first, let's do the line integral. So in order to do the line integral, what's the first thing we need to do? We need to identify what is the curve. So for the curve, we know that we're on the surface, z equals 4 minus x squared minus y squared, but we're also specifically on the boundary of the surface. And the boundary of the surface is where z equals 0. So plugging in z equals 0, that just gives you x squared plus y squared equals 4 if you solve it out. So there's your c, and clearly that's a circle radius 2, and we know how to parameterize that. X equals 2 cos t, y equals 2 sine t, and we're already given that z equals 0. And then we take, in this case, I'm using t for theta, it's the same idea. And in this case, as always, we take t going from 0 to 2 pi. And then we can also calculate dr, which we'll need. So that is just negative 2 sine t, 2 cos t, comma 0, all that times dt. And then we can also write down the parameterization for the vector field just by plugging these things in. So the vector field is going to be 2 times 0, which is 0, and then 2 cos t, and then 4 sine squared t. So now we've got everything, and now we can just plug it in and do the line integral. So your basic line your basic line integral, integral around the curve of f dot dr. We know that f is the first thing we plug it in. We know dr, plug that in, and we know the bounds, t goes from 0 to 2 pi. And so now you've got an integral that you can actually just directly calculate. So we take the dot product, just get the integral of 4 cos squared t dt. And we know we need to use the double angle formula to do that. So you wind up with the integral from 0 to 2 pi of 2 plus 2 cos 2t. And then doing the integral, you get 2t plus sine 2t, plugging in from 0 to 2 pi, and you just get 4 pi. So that's straight ahead, just doing the line integral. Now, let's do the, what should be equivalent, double integral, which is the surface integral. So the surface integral is, we know the first thing we need to do is we need to calculate the, we need to make a parameterization and find the normal vector. However, the surface is described by z equals f of xy, so we have our shortcut to find the normal vector. Normal vector is just negative df dx, comma negative df dy, comma 1. So in this case, that's just 2x, 2y, 1. And we can, and the vector field is essentially already parameterized in terms of x and y. We just need to substitute for z. And then further, we know, well, just thinking about what this, what the shape could be, we already know that the boundary is x squared plus y squared equals 4. So the region is inside that. And for Kelvin-Stokes theorem, we don't need the vector field itself, but what we need is the curl. So if you calculate the curl of the vector field, calculate, you get 2y, comma 2, comma 1. And now plug it in and calculate and see what we get. So it's the double integral over the surface of curl of f dot ds, which is just the double integral over the region of curl of f dot the normal vector dA. So plugging in the curl of f was 2y, comma 2, comma 1. The normal vector was 2x, comma 2y, comma 1. So taking the dot product, we get this. So that's the double integral of this function dA. Now, how do we want to do this double integral? Because the region that we're integrating over is a circle, it'll be easier to do this in polar coordinates. So let's switch it out. So x is going to equal r cos t, y equals r sine t, and we know that it's a circle centered at the origin of radius 2. So we know that r goes from 0 to 2, and t goes from 0 to 2 pi. And we know that dA becomes r dr dt. So making those substitutions gives you this integral right here. And so now we need to, well, first distribute the r, and then that gives you the integral that you need to calculate. And then first we're integrating dr. That gives us r to the fourth cos t sine t plus 4/3 r cubed sine t plus r squared over 2. Evaluating r goes from 0 to 2. So plugging that in, you get 16 cos t sine t plus 32 over 3 sine t plus 2, all that times dt. And then we just need to integrate with respect to t. Integrating 2 with respect to t is easy. Integrating sine t will be easy. And then for the first one, 16 cos t sine t, just do a substitution, u equals sine t, du equals cos t dt. And working that all out, that gives you 8 sine squared t minus 32 over 3 cos t plus 2t, plugging in from 0 to 2 pi, and you get 4 pi. As you can see, doing it either directly doing it by the line integral or doing the surface integral, which is of the curl, gives you the same answer. So we see in this particular case how Kelvin-Stokes theorem, doing either one gives the answer, same thing. Okay. So now let's use Kelvin-Stokes theorem where we're just going to actually only do it one way because it's helpful. So the idea behind when we're actually going to implement Kelvin-Stokes theorem in practice is that, as we've seen before, we're asked to do one integral which might be hard, but the other integral might be easier. So sometimes we're asked to do the line integral is hard, so it's easier to do the surface integral. Sometimes the surface integral is hard, and it'll be easier to do the line integral. So let's take a look at our next question, example. Okay, so use Kelvin-Stokes theorem to calculate the line integral for vector field f equals negative y squared x z squared, and C, the curve, is the intersection of this plane y plus z equals 2 and the cylinder x squared plus y squared equals 1, all with the usual orientation. Okay, so notice that we've got a plane that's tilted at an angle intersecting with a cylinder. So that's going to, if I could just take a moment just to scroll down, let's only focus on the graph. So just looking at only the graph for a second, notice that what this is going to give us is when a plane intersects with a cylinder. If the plane is flat, obviously we get a circle. But if the plane is tilted at an angle, we're going to get an ellipse, but you're also going to get an ellipse that's tilted at an angle. So writing down the formula for that ellipse is going to be fairly nasty. So if we try to write down the equation, the parameterization for that. So the very first thing we're going to do is we're going to use Kelvin-Stokes theorem so that we don't have to do the line integral itself. So let's take a look. So if we want to do the line integral over the curve f dot dr, by Kelvin-Stokes theorem, C is a closed loop. Therefore, this is the double integral over the surface of the curl of f dot ds. And then, of course, to calculate this, we know this is just going to be the double integral over the region of curl of f dot normal vector little n dA. So now I have to go about figuring out these things. So first of all, curl of f, that's straightforward to figure out. So calculate the curl, do, and you get 0, 0, 1 plus 2y. That's the first thing. Second thing is we need to express what the surface is. So what is the surface before we start talking about the parameterization and dA and R? So note that S can be any surface for which C is the boundary. That's going to come in handy later. Now, in this case, the easiest one is just the piece of the plane that we already had in this problem. So in this case, we can describe our surface using the formula, which is y plus z equals 2. And of course, we can rewrite that as just z equals 2 minus y. Well, knowing that, it's now very easy to write down the normal vector. Z is a function of x and y, so we can use the shortcut formula. Normal vector is just negative df dx, negative df dy, comma 1. And working that out very quickly, that is just 0, 0, 1. And furthermore, the region R, which again, remember, is written in our parameters, which in this problem is just x and y. So those are bounded by the cylinder. Therefore, the region is just x squared plus y squared is less than 1. So plugging it in, we know what curl of f is, we know what the normal vector is, and we know what our region is. So plugging in the first two things, the curl of f dot the normal vector, once you calculate that, you just get 1 plus 2y. And then as a separate step, let's figure out how we want to express the region and how we want to express dA. So because the region itself is a disk, it's going to be easier to do this in polar coordinates. So let's do that. So we know that dA becomes r d theta, and the boundaries of the region, let's see, the rate, it's centered at the origin, and the radius is 1. So we know that r goes from 0 to 1, and theta goes from 0 to 2 pi. And then we need to make those we need to go back and make those substitutions. So for y, we just plug in sine theta. Excuse me, r sine theta. And that finally gives you an integral that you can go ahead and directly calculate. So first distributing r, you get the double integral of r plus 2r squared sine theta dr d theta. And now we just go ahead and do it. So first integrating with respect to r, half r squared plus 2r squared over 3. Excuse me, 2r cubed over 3. Times sine theta. Evaluate from r equals 0 to r equals 1. And that gives you 1/2 plus 2/3 sine theta d theta. And now integrate with respect to theta. That gives you half theta minus 2/3 cos theta, plugging in theta from 0 to 2 pi, and you just get pi. So let's take a look back at this problem and understand what happened. We were originally given a line integral to do right here. However, writing down the formula for the path was going to be really, really tricky. So instead, we just convert it using Kelvin-Stokes theorem into a surface integral, which then winds up being something that we know how to do, and it winds up being, at the end, the integral itself is very, very straightforward. However, to get to the integral, we had to do a couple of transformations. So first of all, we know we need to write down the parameterization. So we need to rewrite the integral dA. That's the first thing. And then the second thing was, once we write down the integral dA, once we figure out the boundary, figure out the normal vector, write that all down, then we realize that because the region itself is a disk, we should do this not in terms of dx dy, we should convert this into polar coordinates. So there's a couple of sort of strategic steps in the process of doing this problem. And once you've done all those things, then you can go ahead and directly calculate the integral. All right, another example. Use the Kelvin-Stokes theorem to calculate this surface integral, the double integral over the surface of curl of f dot ds, where here's our vector field, xz comma yz comma xy, and the surface S is the part of the sphere. So the sphere x squared plus y squared equals x squared plus y squared plus z squared equals 4. Inside the cylinder, x squared plus y squared equals 1 with z positive. So, and again, I just want to scroll down just to show you the picture for a moment. So first of all, you can imagine the sphere, and then there's a cylinder that kind of shoots up the middle of it, and we want z positive. So we're basically just taking, and so the part of the sphere inside the cylinder is like a little cap on top. And so that's in the illustration, that's presented in blue. Okay. And we only need z positive, so I just threw away the bottom half of the sphere. We don't need to look at it. Okay. So now, to do the surface integral, so here's what would be the hard thing. The hard thing would be if we tried to do the surface integral directly. Why is that? Well, we know how to write down the parameterization of the surface. However, what are the boundaries? We've basically cut off the sphere at some kind of random spot. We'd have to sort of figure out where we've cut it off. So instead of doing that, we're going to turn this, using Kelvin-Stokes theorem, into a line integral. So we know that the double integral over the surface of the curl of f dot ds is the same as the line integral over C, where C is the boundary of vector field f dot dr. So we've converted the original integral that we have to do, which was a surface integral, into the line integral. So now we're going to focus on doing the line integral. So what is that path? So let's figure it out. So we know two things. We know that that path is the intersection of these two shapes. So it's the intersection of the sphere, x squared plus y squared plus z squared equals 4, and also the cylinder. And the cylinder says x squared plus y squared equals 1. Well, make the substitution, and you can see that 1 plus z squared equals 4. So you can quickly solve that and get z equals radical 3, taking the positive value because z is positive. So we can pretty clearly see from the picture that the intersection is going to be flat. It's going to be horizontal, I should say, and it's where z equals rad 3. So we're just going to get a circle. And that's sort of a visual thing. Let's see. Well, it has to be a circle because, yeah, sorry. So I should say visually it should be clear that what you're getting is a circle from that intersection. So we get x squared plus y squared equals 1, and we're getting z equals rad 3. So that tells you what the shape is. It's a circle at the given height. So we can write down the parameterization. Z is rad 3, so that's that coordinate. And then in the x and y coordinates, it's radius 1. So x equals cos theta and y equals sine theta. And of course, theta goes from 0 to 2 pi. And then we can figure out dr, negative sine theta, cos theta 0. D theta. And now that we have the parameterization, we can also parameterize the vector field. So taking the original form of the vector field and plugging in, we get cos theta rad 3, sine theta rad 3, and then cos theta sine theta. So now that we have everything parameterized, we can now just go ahead and plug in and do the line integral. So the line integral, so the original surface integral equals the line integral, and the line integral equals all of this. Taking the dot product, you get cos theta rad 3 times negative sine theta. Then you get sine theta rad 3 times cos theta, and then plus, and then the last bit is 0. So all of that times d theta, and then the boundaries, as we know for theta, must be 0 to 2 pi. And when you calculate this, oh, everything cancels and you just get 0. So the final result is 0. So the integral, once you've got the integral set up, you can actually, the integral is actually very, very easy to do. Of course, the setup, you can say, is the hard part.
So sorry, Professor. So we don't have to do any.
So notice that in this problem, we started with, we're being asked to do a surface integral. But trying to set up the surface integral was going to be a little bit tricky. So instead, we used Kelvin-Stokes theorem to convert it to a line integral. So this was in the opposite direction of the previous problem. Okay, let's look at another example. So use the Kelvin-Stokes theorem to calculate the double integral over the surface of vector field G dot ds, where G is this vector field, that complicated expression, and the surface S is the hemisphere. So we got x squared plus y squared plus z squared equals 9, where we're taking z positive with the usual upward orientation. Okay, so once again, notice that we could just try to go ahead and directly do this surface integral. However, because your surface is a sphere, you'd probably want to use spherical coordinates, or part of a sphere. You probably want to use spherical coordinates. So if you set it up that way, look how complicated this thing is going to become, just based on the vector field that you've got right here. So an alternative to that is, let's use the Kelvin-Stokes theorem. So what does Kelvin-Stokes theorem tell us? So notice that in order to use the Kelvin-Stokes theorem, we're going to need the fact that G is actually the curl of another vector field. And that's the hint. The hint is that take this vector field and its curl equals G. So if we call that vector field F, we now know that we're trying to do the surface integral of the curl of F. And so then by Kelvin-Stokes theorem, that is just going to equal the line integral over the curve C of F dot dr, where C is the boundary of our surface. So what is the boundary of our surface? Well, the surface was x squared plus y squared plus z squared equals 9. And then for the boundary, so z greater than 0, so the boundary is z equals 0. So making that substitution, you just get that the curve is x squared plus y squared equals 9. So clearly that's a circle of radius 3, and we know how to write down that parameterization. So we've already got z equals 0, so then r equals 3 cos theta, 3 sine theta, 0, with theta going from 0 to 2 pi. And then we can calculate dr. And then we can also plug in to get the parameterization of the vector field. So plugging those things in, we get this expression, where I didn't simplify yet. And so plugging that, so now we're going to do the line integral, but we're going to write it parametrically. So writing it parametrically, we get the integral, and we know that theta goes from 0 to 2 pi of vector field, which is this, dot dr, which we calculated is this. So now, taking the dot product and simplifying, we just get negative 18 sine squared theta. So now we go ahead and do that. Notice how doing these transformations has given us a really, really simple integral to do. Much easier if you think back than what would have been the original surface integral as a surface integral. Okay, so now to integrate this, we have to use the double angle formula. So this is just negative 9 plus 9 cos 2 theta. So integrating that, we get negative 9 theta plus 4.5 sine of 2 theta. And then we just plug in from 0 to 2 pi. So plugging in, you get negative 18 pi. And that's your answer. So I firmly believe that the best way to get used to Kelvin-Stokes is just to do a bunch of examples. So let's keep going with some more examples. So let's use Kelvin-Stokes theorem to calculate the line integral for this vector field, f equals yz, comma 2xz, comma e to the xy, and c is the circle, x squared plus y squared equals 16, where z equals 5. So we could just go ahead and try to do this line integral, but let's turn this into Kelvin-Stokes theorem and see what happens. Let's use Kelvin-Stokes theorem to turn this into a surface integral and following the tip, and let's see what happens. So we know that in order to do this integral, we're going to have to convert it using our typical surface integral techniques. This is going to be the double integral over the region of curl of f dot the normal vector and dA. So now let's go ahead and try to do this. So first we're going to need the curl of f, and then we're going to need the normal vector. So curl of f, if you calculate it, you get x e to the xy minus 2x, then y minus y e to the xy, comma z. Now that does not look any better, but just wait. Next, we need to calculate the normal vector. So for that, we need to know what is our surface. So we're not actually given a surface. We're only given the curve C. But the only thing that we need is we need C to be the boundary. So S can actually be any surface for which C is the boundary. This is awesome. We can choose any surface we like. What is the easiest surface for which C is the boundary? Well, C is a circle that is sitting flat horizontally at the height z equals 5. So what's the easiest surface there? The easiest surface is just z equals 5. Of course, with that circle being the boundary. So our formula, so z equals 5 is just our surface. Or to be precise, it's the flat disk at z equals 5. So the formula for the surface is just z equals 5. So what is the normal vector? The normal vector is just negative dx, negative df dx, negative dy, comma 1, but df dx and df dy are both 0. So the normal vector is just 0, 0, 1. So this is one of the slickest things that we can do with Kelvin-Stokes theorem. We can use any surface as long as C is the boundary. So the region itself is just the region of that surface bounded by the circle. So x squared plus y squared is less than 16. So setting this up, we want the double integral over the region of the curl, which was that vector field, dot the normal vector, which we just found was 0, 0, 1, and then all of that dA. Taking the dot product, you just get z. And furthermore, because we're on the surface, we already know that z equals 5. So finally, that's the double integral over the region of 5 dA. We know that that is just 5 times the area of the region. And because the region was a circle, or to be precise, the region is a disk, the boundary is a circle, of radius 4, we know what the area is. It's just pi times 4 squared. And so 5 times pi times 4 squared is just 80 pi. So in this case, because we wound up with the double integral of dA, we just know it's the area. And then multiply by 5. So this winds up being a case where using Kelvin-Stokes theorem is actually a super duper shortcut that gives us something very, very easy to calculate. So at this point, we've done a number of examples where we've used Kelvin-Stokes theorem to calculate an integral, either converting a line integral into a surface integral or converting a surface integral into a line integral. So what I want to do now is I want to make some observations about Kelvin-Stokes theorem sort of be more sort of broad view in nature. So first thing, well, actually first a tip about solving problems using Kelvin-Stokes theorem. So the first thing that I recommend is that it's going to help to draw the graph. So yes, the graph may be three-dimensional and it'll kind of have to be a rough sketch. But it will help you, even if it's just a super rough sketch, it'll help you coordinate the surface S and its boundary C. And it sometimes it might also help you think about what are the boundaries, either for the region or for the curve. Okay. And the other thing is that a lot of the time, you've got one equation defining the surface and then a separate equation that defines the boundary, or maybe there's an intersection. So you need to take both if you want to define C. And then usually you can do some kind of substitution and simplify. And then also it's helpful to note that a region or a surface sometimes is represented with an inequality, but an equality sometimes represent the boundary. So it might be helpful to think about those things as well as you're doing these problems. So some comments. So just a call back to the fundamental theorem line integrals. So with FTLI, you're being asked to do basically some line integral. So you've got a vector field and you've got to do a line integral. And then what you would do is you'd say, oh, you'd figure out that it's conservative. Therefore, my vector field F is the gradient of some function F. And then you'd solve for the potential function F. And then you could finish the problem F of B minus F of A. With Green's theorem, you'd be given some function F inside a double integral. And then you'd need that the swirl of vector field F equals the function F. And then you would solve for what vector field F was in some of the problems. Now, with Kelvin-Stokes theorem, you have to do one direction says do the surface integral of some vector field G, and then you need to find, as we saw in one of the last problems, you need to find F so that the vector field F so that the curl of F equals G. So this is actually a new thing. Now, F is called the vector potential. The vector field F is called the vector potential of vector field G. Now, in all the problems here, vector potential F was given. So either it was just written as curl of F, so you didn't even need to think about, well, what is the curl of this vector field G? You're just given the original vector potential. Or in the last problem, you were told that here's vector field G, and here's the other vector field, and curl of the vector field is G. So you were given the vector potential. Now, what if F was not given? What if you only had your original vector field and you define its vector potential? Define the vector potential requires some additional techniques. So I have a description of that written elsewhere, but it's important to know that find the vector potential, if you had to do it, is actually kind of a fancy thing. It is quite a bit harder than finding potential function F. And so for our purposes, we're not going to do it. But if you do have to do it, there are techniques that are available for doing that. Okay, that's one comment. Another comment I want to make about Kelvin-Stokes theorem. So I want to think about the special case where S, instead of a surface that exists in three-dimensional XYZ space, what if S is actually flat and lies in the XY plane? So in this case, the surface S, because it's in the XY plane, we can really just think of it as a region R. And as always, the parameters would just be x and y. And notice that the unit normal is therefore just the k vector, or in other words, 0, 0, 1. So because of that, the surface integral will become a two-coordinate integral, meaning ds equals dA. And Kelvin-Stokes theorem just becomes, let's check it out. So the line integral, the integral around the curve of f dot dr by Kelvin-Stokes theorem, becomes the integral over the surface of the curl of f dot ds, which by our techniques we know is just the double integral over the region of the curl of f dot unit normal n ds. Now, unit normal n is just the k vector. Well, what happens when you, and ds is just the same as dA because they both live in the xy plane. And what is the curl of f dot the k vector? Remember, that just pick the k, dotting with the k vector is going to pick off the third component of the curl. And what is the third component of the curl vector? It is just the swirl. That's something that we saw before. So this winds up being equal to the double integral over the region of the swirl of FDA. And that should look super familiar. That's, so knowing that the line integral equals that, that is just Green's theorem. So take a look at that. Green's theorem is really just a special case of the Kelvin-Stokes theorem. Next, so knowing that Kelvin-Stokes theorem is like a general version of the Green's theorem, we can use that to help us understand what Kelvin-Stokes theorem is saying by just remembering that's like sort of like a higher dimensional, fancier version. So what this tells us is that the total, so remember that swirl is like two-dimensional circular motion and the curl measures three-dimensional circular motion, remembering back to what these vector field operators represent. So this tells us that Kelvin-Stokes theorem says that the total circular motion within the surface due to the vector field is the same as the movement along the boundary due to the vector field. And of course, the vector field does not need to represent movement, but using that as one application or as a metaphor. So break it down like this. So on the left side, we've got the line integral, and on the right side, we've got our surface integral. So so integral gives us the total motion. I'm thinking of f as representing motion. That's just one idea. And then dot t is along the boundary. Or you can think of it as dot dr, same idea. And that equals the double integral of the surface is the total. And then remember that curl f gives you the circular motion. And then dot n gives us the component within the surface. Now that seems a little weird. Usually dot n gives the perpendicular component. But remember, look at the last comment there. Dot n gives the component within the surface because remember that the direction of the curl is the axis of the motion or of the swirling action. So in other words, curl sort of points in the direction perpendicular to the motion. So this is one way to sort of think about what the Kelvin-Stokes theorem says. So coming up, I'm going to give you another way to conceptually understand the Kelvin-Stokes theorem. So what we're going to do is we're going to zoom in and sort of look at what Kelvin-Stokes theorem means at a point or in a very, very, very small region. So first, let's start with the Kelvin-Stokes theorem, written out with the dot n. And now let's think about it this way. So what if we're at a fixed point, P, that in our surface? So now let's take a small disk with a radius A. And so that's going to give us, so we're going to call that thing S sub A. And that's going to have a boundary circle, C sub A. So since the disk is small, then the value of the curl is approximately constant over our entire disk, which is over our entire little surface. So let's make an approximation. So let's take the line integral over our path C sub A of f dot dr. And then by Kelvin-Stokes theorem, we know that's the same as the double integral over our surface of the curl of f dot unit normal n ds. Now, because we're on this tiny, tiny region, we're saying, well, let's say that the curl of f approximately is constant, and then the normal vector approximately is constant. So what does that give us? The double integral over our little surface, our little disk, curl of f at our point, dot the unit normal at our point, ds. But if the curl of f is a constant, and then the normal vector is a constant, then that dot product itself is a constant. And then we're just left with the double integral of ds. And double integral of ds is just the area of our surface. So the area of our surface, since it was a disk, is just pi r squared. And our radius was a, so it's pi a squared. Now, of course, that was an approximation. If your radius is infinitesimal, so you have an infinitesimally sized disk, an infinitesimal sized surface, then this approximation becomes exact. So then we can say that the line integral, the integral over the curve c sub epsilon of f dot dr is equal to the curl of f at our point P dot the unit normal at our point P times our infinitesimal area, which is pi epsilon squared. Another way to say this is using limits. So moving the area to the other side, so all epsilons are on the same side, the limit as a goes to 0, 1 over the area pi a squared, times our line integral over our little path c sub a of f dot dr equals the curl of f at the point P dot the unit normal at the point P. So let's put that all in words. So the circular motion within the surface, and that's just the normal component of the curl, is the flow along the boundary, which is our line integral, divided by the area, or in other words, per unit area. And here we've got this relationship expressed around a single point P, or similarly, we could think of it as expressed at an infinitesimal region around the point P. So all of this is kind of a deep way to understand what Kelvin-Stokes theorem is saying. And if you have difficulty thinking about it in these terms, remember that this is just sort of a parametric or one extra dimensional version of what Green's theorem was saying. And now I'll make one more comment. So some long time ago, we said that if the curl of vector field f equals 0 on all of R3, then f is conservative. We said we'd have to wait if we wanted to prove that. So now that we have Kelvin-Stokes theorem, we can finally do this proof. And with Kelvin-Stokes theorem, it's actually very easy. Let's take a look. So first of all, every closed path C is the boundary of some surface S. So that's possible to prove, but we'll just say that intuitively, this is obvious and it makes sense. So therefore, for any closed path C, we have that using Kelvin-Stokes theorem, the line integral around C of f dot dr equals the double integral over the surface, for which it's a boundary, of the curl of f dot ds. But we're given that curl of f equals 0. So that's just the double integral of 0 vector dot ds. So that, of course, has to be 0. So previously, we saw that if the line integral of f dot dr equals 0 for every closed path C, if that's true, then f is conservative. But we just showed that that's true. Therefore, vector field f is conservative. And that completes the proof that we started a long time ago. Okay, so that was Kelvin-Stokes theorem. So let's just take a moment to sum up in broad strokes what we know. So here's Kelvin-Stokes theorem. Ta-da. The integral over the curve curve C of f dot dr is the double integral over the surface S of the curl of vector field f dot ds, where your one-dimensional curve C is the boundary of a two-dimensional surface S. And then there's an alternate form for Kelvin-Stokes theorem. And then we continue to use the fact that D-oriented S is, by definition, unit normal n times ds, which when we convert it into parametric form will be normal vector n dA. And then finally, we have a way to understand what Kelvin-Stokes theorem is saying in words. The total motion due to the vector field along the boundary is the same as the total circular motion within the surface. And that's an overview of the Kelvin-Stokes theorem.